know we're going to start. Podemos avisar a la gente que está fuera para que venga. And since we are the last session, I think we have some buffer maybe in case we need to extend a couple more minutes. Okay, so let's get started. Welcome, everyone. As they say, all things come to an end. We're getting close to the end of this symposium. This is the last session, but we have very exciting and interesting presentations coming up. In fact, we have one keynote and 3 plenary talks. In the sense of the logistics, just to remind you, as we have in the previous sections with this type of setting, we have about 30 minutes for the keynote. It's broken down in 20 minutes approximately for the presentation and 10 minutes for Q&A, followed by 3 plenary talks in which we have about 20 minutes for each, 15 and 5. My name is Borja García de Soto, an assistant professor from New York University of Abu Dhabi, and I'm happy and honored to be hosting this last session of the symposium. So without further ado, let's maybe start with the first presenter. I believe Frederic Bosche is going to be presenting building information model preprocessing for automated geometric quality control, the work done in collaboration with Martin Bueno. Fred. Thank you very much.
Thank you, Bora. So first of all, yes, this is a work that is led by Martin. He couldn't be here today, but it's my pleasure to present this work that we've done together. There you go. So this work is done as part of the EU-funded project called Cogito. Cogito is actually one of a series of sister projects that work on similar topics, actually. And the goal of Cogito is to create a digital construction 4.0 methodology, really a toolbox. Okay, so I'll wait that person finishes. Is it okay? So that makes use of various information to deliver information and knowledge that is useful for project managers and other professionals involved in construction project delivery. So it uses as-planned information, and as you would expect, building information modeling, so including geometry, but also augmented with schedule information and other information like cost data. It uses as-is information, or let's say data, captured using reality capture technology. We employ various types of technology, and all this data is processed and ingested in the digital twin platform that we create, and the digital platform stores that using linked data approach. I can detail a bit more about this, but it's not going to be the focus of my presentation today. And all this data, which is linked together logically, supports a number of applications related to health and safety. So first of all, secure workflow planning and monitoring, dynamic safety planning and monitoring, real-time visual and geometric quality control. And all these, the results of these, which are stored again in the digital platform in a structured way, can be visualized using IT off-site and on-site visualization technology. The focus of my presentation today is about the automated geometric tolerance compliance control. And these are the tools, let's say, in the tool chain that are involved in this. So we make use of the 40 beam model as input to understand what quality control needs to be done and where and when. And then we employ reality capture technology, particularly 3D laser scanning, to capture what has actually been done. And then we compare both using typical processes that you've seen in the past. And this enables us to inform the project management team which geometric quality control is passed or failed, and therefore they can decide to take actions. So this is going to be the focus of my talk, in particular the offline, what we call the offline part. Is it microphone not working well? The offline part, which is about the processing of the 40 beam data. But generally, I should say, yeah, there is a what we call the offline and the online part. The offline part is what happens during the planning stage. So you get a 40 beam model, and you want to plan what is the geometric quality control that needs to be done. And the output of that is just a list of geometric quality control tasks that need to be conducted throughout the project. So the questions that this is trying to answer is actually what QC needs to be conducted and when. There's another aspect of planning, which is what data acquisition does it require? So once you know what you want to control, then you need to plan how you are going to acquire the data and how to best acquire it. But this is not, won't be the focus of that talk. And then when you actually deliver the project, you know the tasks that has to be done. You inform you have to do quality control for columns X, Y, Z. You acquire the data in the form of the as-built point cloud, and you automatically apply the quality control rules in order to identify which rules have actually passed, failed, or maybe simply could not be controlled because of inadequacy of the data. So I've focused first on the first part here. So to answer the question, what QC needs to be conducted and when, quality control or quality specifications are provided for each project. Some of them may be specific to a given project, but many of them are also actually specified in standards. So here we focused on some of the standards, and in particular one of them. I give you two here. On the left-hand side, you have a European standard on the execution of concrete structures. And I'll show you an example of its content. And on the right-hand side, we have the same for steel structures. Actually, steel and aluminum structures. So if you take the concrete one, inside you will see a number of tolerances that are defined for various geometric distances or other relationships. So here I show you two related to walls and columns. And the first one is about the inclination and verticality of that wall or column. And the other one is about the alignment of stacked columns or stacked walls. These are all, by the way, driven by structural performance. Because if your column is a bit tilted, then loads won't be passed correctly, and therefore the structure will not behave as expected. And same for the stacked columns. And you can see here, there's a description, and then there's a tolerance. That is not necessarily a fixed value, but that depends on the context. Okay. So we took those rules, and the way the industry works right now is like those rules only exist in PDF form. They are not digitalized. So if you couldn't, they are not ready for a digitalized industry. People just know those rules by heart, it seems, and they kind of try to apply them. Not all of them, certainly, and I'll give you an example why. But interestingly unstructured, and I'd like to know more from professionals doing this actually. But certainly, we have this aspect which is unfortunately not digitalized at all. And certainly there's a need to digitalize those rules. We have done such an effort here, but I think this is something that should be done actually probably by the standards organizations. They should not just provide a PDF version of those rules, but some sort of IFC compliant expression of those rules so that we can easily apply them to BIM models. So we did it here, but I think this is an effort that should be done at a higher level. So we created a dictionary of quality control rules extracted from those documents. And for each rule, we have a quick description. This is for us humans to be able to remember which rule is what, because we give it an ID, but once you have an ID, you really don't know what it is anymore. So we know where the rule comes from, the source document, the source section, a quick description. Then much more important, we have the rule context. And this is where we define where this rule applies. And here we define what is the type of components that it applies to. So for example, applying IFC type object descriptions like IFC walls or IFC columns or IFC slab. We also define what material this rule applies to, because the tolerances for verticality of columns is not the same for steel columns or for concrete columns. So we need to be able to distinguish them in the BIM model. And also what are the relationships that are important, because a lot of times those rules don't apply to a single object, they apply sometimes to a pair of objects. So for example, the stack columns, we need to say this rule applies to cases where columns are stacked on top of each other or walls are stacked on top of each other. There are also tolerances for the spacing between columns. And so you have to identify neighboring columns. So this is the context, it defines the context where the rule applies. And then we have the rule code. So essentially, when we identify this context and we have the as-built data, then we know how to compute the distance so that we can compare it against the tolerance. So just to give you take my two examples from earlier, we translated those. It looks a bit horrible. We have this typically in JSON type formats, but you can see here we have a rule one, the source, where it comes from, what is the component type it applies to, so wall or column, what is the material, concrete. There's no particular relationship because this applies to a single component. But if you take the second rule, here we have a relationship which we have encoded as above, below, but you could actually say stacked, for example, so on top of each other. So to date, we've encoded 15 of those rules from the concrete standard. So you can see here we have inclination, which I just presented, curvature of columns and walls, location of columns and walls at any story, cross-section dimensions, things like this. So I should say we encoded those rules, context in particular, not necessarily the application for all of them. These are the rules. And now what we want to do is give me a BIM model. This is what I have to build. And I will process that BIM model. And I will try to identify, okay, where each rule applies in the BIM model. Okay, so we take an example here. This is a Revit model that some of you may be familiar with. It's on the, it's one of the examples on the Revit website. And you can see that BIM model contains, 350 columns, 190 columns, concrete beams, sorry, 195 concrete columns, 6 concrete walls, and 5 concrete slabs. There's a problem with the, okay, there's a missing something. And so what we want to identify here is the relationships that are listed at the bottom. Adjacency within story, physical connection. So for example, beam and a column will be connected and their tolerances are related to the connections of beams and columns. The above, below, the stacked relationship, and story adjacency. So this is more which slab is on top of another one. These relationships, they are necessary because they appear in the 15 rules that we have encoded. Okay, but importantly, these relationships, they don't exist in the BIM model. Okay, so BIM models do not contain natively this kind of information in them. So what we have to do is take the IFC model and process the geometry and try to infer where those relationships appear. Okay, and this is, we can show the results to you in the form of a graph. Okay, so here in this graph, the red circles are the columns, the blue circles are the beams. The walls appear somewhere there. There are only 6 of them, so a bit scattered. And they are in a little island somewhere. And we have also the concrete slabs in the same situation. And then we have the connections, which are colored just like on the right-hand side. So now we have all these instances of columns and the components we care about. And we have all the instances of the relationships. And thanks to that, now we can exactly extract where each of those 15 rules apply in the BIM model. And just to show you an example here, if you click on one of the buttons, we can show you in the BIM model, this is that column. And that column here is actually connected to 2 beams, and it has a number of neighboring columns. Actually, there's too many in these slides. We've actually improved it, but we wanted to stick to the content in the paper at the time of submission. Now we would actually have more like 4 neighboring columns because these are the ones that the rules actually applied. And then we can show you the results. If you take the quality control rule 1, inclination of columns, well, there are 195 instances of this because there are 195 columns in the model. But you can see just from those 15 rules, they appear quite a few times. And if you were to do the quality control, geometric quality control for this project, just for those 15 rules, and that's not all the rules inside the document, you need to nearly 10,000 quality control instances. I'd be curious whether construction companies actually do that many checks on a project like this. My suspicion is that they focus on key ones with the assumption that if you pass those ones, you pass the others. But that might actually be wishful thinking. But they do that because clearly they would spend a lot of time doing all these checks. So to give you 2 examples, this is an instance of the quality control rule 1. It's an instance, so it refers to one of the rules, okay? And this is how it's encoded, by the way, in our digital twin graph. So we have instances of rules that refer to instances of quality control tasks that refer to instances of rules. And we have another instance here where we know the components, we know the rule, but obviously at this stage, we don't know the result of the quality control. So the lines in red, we don't have yet. We don't know when the quality control was actually conducted. We don't know the results. We don't know the outcome, I should say, pass or fail, and the dimensions related to the tolerances. So now we go on. We know what we have to control. Oh, and by the way, we actually know when the components in the BIM model will be built because we have a 4D model. So we actually know when each quality control rule instance will have to be conducted during the delivery of the project. So not only we have a big list, but we know throughout the project where each item is to be checked. So now we finish construction of, let's say, columns ground floor. And there is a task that is issued to the surveyor. Please go survey the columns ground floor, because there's a number of quality controls instances that need to be done for the related to the columns ground floor. We go acquire the data. Now, obviously, you need to acquire the whole geometry of the components. We use terrestrial laser scanning, but obviously there are lots of emerging technologies, and we've seen a lot of them already in the last 2 days. Importantly, we work with fixed stations, and the reason why we do that, it's because if you look at the values of the tolerances that exist, At this moment, I believe, only fixed station to laser scanning can give you the accuracy you need, or the certainty you need in the value in order to have some reasonable results. But the future, will probably change that. Certainly, we're looking at using robotic stations where they can just move around, but just become fixed stations and just take a scan, but not mobile laser scanning, for example. Then we look at the as-built geometry. Now, at this stage, we're only looking at the pose, so not necessarily variations in the shape. And that's something that is an interesting research topic. And at the moment, we're looking at various things, but we are using the traditional approach of, I have the point cloud for that column. I have the point cloud in the project coordinate system. I have the location of the plan column. And then we try to match them. And once we match the points, we apply some ICP type algorithm to essentially move the planned object in order to put it in its as-built location. Okay, so it's not like, we still have the planned location. We start from the planned location to identify where it is really once built. And then once we have the as-built geometry for the components, then we can apply the code, right? So we say the stack column, for example, once we have found the as-built position for both columns, then we can look whether these two moved geometries are on top of each other within tolerance. So I think we have a couple of examples here. We haven't done this on site yet. Actually, that might happen soon. But at the moment, what we did mostly is that we simulated points laser scans. We simulated some errors in the construction and generated point clouds from those errors. And then we saw, what happened to our process. And so here we have an example where we had perfectly built columns. So obviously you would expect when you laser scan, they come on top of each other. I should say we did do perfect point clouds in the sense that the components were built exactly where they were planned in that case. But we did add a lot of noise to the point clouds, etc., to try to simulate a realistic point cloud. And so for that particular rule, they end up being exactly on top of each other. And so the scalar result was a 0 deviation. The tolerance in that particular case was 15 millimeters. So, it just passed. Now we have another example here where we have a column and a beam. And here there are two rules that actually apply so far that we have encoded. One is that was the horizontality of or levelness of the beam. And then there is the connection between the beam and the column. So the first one is the horizontality of the column. And so here what we had introduced a little bit of deviations. And you can see the deviation here. You can see the point cloud on the left-hand side is a bit above, and then on the right-hand side is a bit below. And that's because there's a bit of tilt. And so once we apply the ICP, actually I realized the pictures don't have the as-built pose. They just show the design pose. But once you apply the method, in that case, you get a deviation, which is measured in meters, which is higher than the tolerance for that particular context. And therefore, there is a fail. But the other one here is about the connection between the beam. So the central line of the beam needs to match the central line of the column. So not shifted to each other. And in that particular case, it was not a problem. It was, there was a 10 millimeter deviation according to the algorithm, but this was actually still within tolerances. So in that case, we have a pass. So I didn't have it as part of my presentation, but this information is actually stored in the digital twin platform. We developed a data model and developing an ontology for storing geometric quality control data, so that then that can easily be queried. And through our interfaces, for example, somebody may want to query, show me all the column verticality results for that project. And that can be easily queried through the graph network that represents the digital twin platform, or show me the quality control for all the columns or specific component or etc. we are about a year and a half into the project, about 3 years, and we are just doing some pre-validation work on site. One last thing I'll highlight, that project is actually focusing on infrastructure. I showed you an example of buildings because the building sector is way more advanced in terms of building technology. And we are dealing with rail, for example, case study. And some of the issues we have is working with IFC 4.3, which has just been released officially last week, I think. We have some other issues to deal with. So for the time being, we've been trying to play with building cases, but actually our validation work this summer will work on railway. So thank you very much. And I'll take any Q&A if there is any time.
Thank you, Fred, for such a nice presentation. I would like to open the floor for questions. Anyone here, please? Yeah.
Wonderful presentation, Fred, as always. 2 questions. In the context of buildings, how often you've dealt with looking to deviations on MEP systems?
Can you repeat deviation that what?
Mechanical, electrical, and plumbing systems. Yeah. And considering the fact that granularity in the model is different, there's more flexibility. One on that, and if you're focusing on infrastructure, especially rail tracks, obviously you need different types of requirements for placement of the rail tracks and embedments, conduits, and whatnot. So if you can comment on the type of things that you've come across that are more interesting from a contractor perspective, that would be great.
Yes. So first, we haven't, our work is focused, so we focused on structural works so far, also because we are doing this in the context of infrastructure. So we were kind of focused on that particular part. So I think the main focus of the paper was actually the planning work. So it's actually planning what needs to be done and lay it out. And that has some consequences, right? If you take a construction schedule, do you ever see in construction schedule a task that says quality control after each construction work, right? But in theory, it's embedded there, it's implicit. So what we do is we create these things, and actually that feeds our workflow modeler that takes the schedule and then splits it into a part of make work safe, do the work, quality control, and each activity. And in fact, there is some further splitting that needs to be done, etc. So it's there's an aspect of that. MEP, much more challenging on the detection and the matching, right? That's the problem where I have a student working on that in different contexts, and that's much more challenging. Structural works tend to be broadly where they should be. And that makes the matching and then identifying the as-built post much easier. Certainly MEP requires much more work, although you would hope that with digitalization and move towards prefabrication of MEP components, etc., more and more, they should be broadly where you would expect them to be. But we have a case with a student where it's China. It's actually a garage place, and they have the MEP, and some of them is great, but then one of the duct is like 0.5 meter away from where it should be, and just 0.5 meter challenges algorithms massively, and different approaches need to be conducted actually. And the second question was about
placement of the rail tracks. I'm guessing you probably get into rebar spacing, embedments, conduits, things that are below the rail track.
So we really just engaged on this. So the things we're looking at is actually the location of the rail itself. So the where it is, the spacing between the sleepers. And we're still trying to get information from the builders, like what are these critical ones. We have, especially an important one we look for to look at is the spacing between the platforms and the rail, because this is for light rail and there is platforms every so often. And this is really critical dimension so that trains don't actually hit the platforms. And also they told us platforms, there's the slopes that need to be there for drainage, etc. So there are some things that we're looking at, but actually we're still trying to extract that information from the builders.
Thank you.
And coding is hard because IFC doesn't have an IFC rail or an IFC sleeper or anything. So we need to work around that a little bit as well.
How robust is the iterative closest point registration to incomplete point clouds?
Can you repeat?
So these the question is about the ICP algorithm, the
Okay.
registration of the point cloud to the BIM model. And you said that you perform the registration on an object to object
Yes.
basis. So the question is, how robust is the ICP registration to incomplete point clouds? These are point clouds where perhaps the entire object hasn't been scanned.
Yes.
Maybe you just have one side of the
Yes.
object scanned. Yes.
So actually, we're doing work. We're doing two pieces of work there. One is we are testing this right now. So we are randomly removing data from the point cloud simulated and see how well the ICP converges to what we think is the correct position. So we're trying to learn, how much data you need in order to get a good result. And that feeds into some other piece of work, which is the planning for scanning work that we're doing right now. So that we can tell surveyors or a robotic platform that to get the right quality data, we need to have confidence in the as-built position. We'll get the robot needs to go here and it needs to go there and get the data. And then when we process the data, we can actually check whether we have indeed the data we were expecting to have in order to do the quality control. And we do have that. We have a branch out that says, data is not good enough. We don't want to give you any results. Just go back and scan.
Excellent. Thank you.
Yeah, thanks.
So I have a question about the constraints that you actually piece out from the standards document. There are 6 gazillion of them, and then you have to determine which one is actually important and actually encodable. Have you thought through how to automate that, or do you automate that process of determining the rank of what is the most important constraint that I want to determine geometrically, or is that still a very manual process?
The standard doesn't say this one is more important than the other. The standard says these are all, and so I talk to contractors, say, do you use that standard? And they kind of they don't really know. But then they go back and say, oh yeah, we use that standard. It's so embedded in practice that they don't really, think about it, that it is that standard. They just know that all of columns, they have, this is the tolerance for a column, or this is they kind of know, but they don't necessarily know where it comes from. And as I say, I don't think they check everything. My suspicion is that they look at the position of individual columns and probably their inclination. And if that's good enough, there is probably an assumption that, the spacing between columns is fine and the stacking is fine and other things are fine.
But I guess my question was, what are your thoughts on the automatability of that process? Because we do this, but we still get it from the expert. They tell us what they care about, and we just try to encode that. But do you think there's a path forward to automate this and figure out from the standards what actually matters and what doesn't?
So good question. Unfortunately, I don't have the slide here. But I think one thing that might be interesting, I showed the graph of the connections between the components and the type of relationships, and therefore where each tolerance apply. And we looked at, for example, what are the key nodes in that graph, right? Because this node is connected to that. Therefore, if there's a little problem with that column, that will have a lot of knock-on effects, right? So we looked at doing this graph network analysis but it's very, very preliminary, and it would I'd probably put a MN students on this next year or something like that. But to actually process the graph and see what are the critical nodes here, because if that column is out of tolerance, then the odds are this will not work, this will not work, this will not work. And there, I should say, there are some people that looked at tolerance chains in construction. There are some work that's done maybe 5 years ago, I think, out of California, that was really interesting, and I think they'll probably apply. There's probably going to be some relationships between these works. Yeah. Thank you very much.
Thank you. Don't forget, we'll have a chance to continue these exciting discussions during the gala dinner later. Moving